Alright, hi again everybody. Welcome to CTM lesson 3.6. And before I forget, I did just have some dinner and I'm kind of bummed out. I have some pie on my shirt. Okay, that's funny, Mr. Wagner. Thank you. I'll be here all night. Some new vocab, just a couple of new terms. Syllogistic argument or syllogism, and this is pronounced not Euler but Euler, an Euler diagram. What that is, we need to know what those are by the time this lesson's done. And then, as always, make sure you check out those extra examples in the book for some more help. Alright, so let's start with symbolic arguments. That's what we've been doing all along in this chapter so far. And now syllogistic arguments is this new idea presented in this last lesson. These guys, you probably recognize this guy from some of the past lessons we had. This curmudgeon is Augustus de Morgan. And this guy also did some symbolic argument stuff. We know him best, well, he was Charles Dodgen, but we know him best as Lewis Carroll. He was the author of Alice in Wonderland, and he did a lot of stuff with logic, a lot of interesting stuff. If you read his books, very intriguing logical arguments that he presents in there. This guy, this is Aristotle. He lived around 350 BC, and he was basically the founder of syllogistic arguments as we know it. And then this guy, this is Euler. This is our main man for this lesson, Leonhard Euler. It looks like Euler, but it's pronounced Euler. Just remember, he didn't actually make oil, but pretend he made oil. This guy was pretty amazing. I just want to read what's in the book about him just a second, and then we'll continue from there. So this is on page 154 in your book. If you want to read about Charles Dodgson and you want to read about Augustus de Morgan, they are on pages 132 and 133 respectively. But this is about Leonhard Euler. So this is just from the book. Swiss mathematician Leonhard Euler from 1707 to 1783 is when he lived, produced such a large volume of work that all of it has not yet been compiled. It has been estimated that a complete edition of his work would make up over 60 volumes. Although his greatest contribution was made in the field of modern analysis, his work also explored physics, astronomy, trigonometry, and calculus. Euler also had a great influence on the notation and symbolism of mathematics, and it was through his work that the symbols E and, yes, pi right there came into common use. His facility for mental calculation and his uncommon memory allowed him to continue his prolific career even after he lost his vision in both eyes. This dude was pretty amazing. So I'm not sure who's going to win this battle, though, the Rock'em Sock'em Robots battle. These two guys, I think they're going to go at it pretty big time. This guy, honestly, he doesn't look very tough. Lewis Carroll, not looking very tough. I don't know about Euler either, but he's got the stink eye going. I think that gives this team the advantage. But let's check out some symbolic arguments versus syllogistic arguments. And what's the difference? What's a syllogistic argument anyways? So let's get my line tool out here. And in just a second, I gotta turn my little slate back on. Are you coming? Yeah, there you go. We got it. Alright, so let's see. We've got, use my line tools here and come up with a nice table this way. So let's put symbolic arguments versus syllogistic arguments. We're going to just make a table down here and fill that in. So make yours kind of like mine. You got the blue lines on your paper. And there we go. That will be good for that, and about like that will be good right there. Let me just make that one a little more parallel if I can. I guess I can't do that. I don't know how to rotate that. That's good enough, I guess, for us. I'll have to figure that one out later. Then we have right here, we're going to put words / phrases used. So we've seen a lot of different words and phrases that come up a lot in symbolic arguments, and now we're also going to see what gets used a lot in syllogistic arguments. And then methods, or the method, over here we'll put the method of determining validity. So determine whether it's a valid argument or not. And then over here we'll put our symbolic argument. So let's put symbolic right here and syllogistic right here. Syllogistic. So words and phrases used. We've seen in symbolic logic, that's what we've been doing mostly in this chapter, completely in this chapter up until now. We had and, we had the word or, we had not, all represented by our different symbols that we've been using. Not, we had if-then statements, and we also had, can you guess it? You remember the other one? If and only if. If you said that, you got it. So if and only if. And then over here, the method of determining the validity, we used truth tables. We used truth tables quite a bit. And then we learned some shortcuts as well. So you had or comparing, or comparison I should say, or comparison to standard forms. Comparison to standard forms of arguments. And then for syllogistic, we've got some new phrases, some new words. We could see something like this: all are. So everything is. All are. Some are. It'd be like at least one. Some are. None are. Some are not. That's another phrase you might see. Some are not. You might see something is a something, or something is not a something. So these are all different phrases you might see in syllogistic arguments. And how we determine if these are true or not, we use something called the Euler diagram. So what's an Euler diagram? Well, we'll get to that and see what that looks like in a second. So very related to some of the stuff we did in chapter 2 with the set theory. We're going to be using some Venn diagrams with Euler diagrams. So let's check out an example here. Is this a valid or invalid argument? Here's an example, our first example of a syllogistic argument. All national parks are cool. Now we're not saying this is necessarily true or false at this point. I think it's true personally, but we're just saying that this is one premise. We're going to assume that if this is true and the next thing is true, then we're supposed to say that conclusion can follow from that. This right here, if you know what this is one of the most amazing places in the world. This is Yosemite National Park. So Yosemite, right here in California. Yosemite is a national park. Yosemite is a national park. I'm going to say those two premises are supposed to allow me to conclude this, if this is a valid argument, that Yosemite is cool, or at least that's what I'm trying to figure out. Is this a valid argument? If this and this were both true, would this have to follow necessarily from those two statements? So how can we figure this out? We can draw an Euler diagram. So let's do that down here. This is an Euler diagram. This is what an Euler diagram looks like. So I'm going to use my shape tools here to make these. No, I don't want red. Don't want to use that. I'm going to use black to start. Okay. And I don't want a square either. I want a rectangle. So let me erase that. There we go. That should do it for me. That's better. All right. There you go, Mr. Wagner. And this is going to be my universe now. This will look familiar from chapter 2 stuff, set theory stuff. So that's my universe. And I know that I'm just going to go with N for national parks. I'm going to go with Y for Yosemite. I'm going to go with C for cool. Those things, I don't feel like I have to label those. I think that's pretty obvious. what would be what. So let's go and now make some circles within my universe here. So let's start off by looking at this. If you ever see an all something, that's pretty easy to start with. So all national parks are cool. So within the context of a cool circle, national parks would have to be completely in the cool circle. So let's draw national parks. We'll say that is, oh, I want to use some different colors here. So let's go with, we'll go with red. I think I selected that. There we go. Go with red. This will be my national parks circle. And I'll draw a little N for, come on. There you go. Draw a little N for red, or for national parks, with the red circle. And we know that national parks are completely within the cool circle. So I'm going to draw a cool circle. I'll use blue for that. And so completely within this blue circle. Doesn't have to be, they don't have to be concentric circles, but I'll just move that so that they are. Okay, so now that just makes it look a little neater. The way I had it before was okay too, though. So now N, it's still completely within the cool circle. The cool circle, I'll go with, boy, I just keep messing up. I'll just go with, I see a little red mark there. There we go, get rid of that. Blue now, that's completely within the cool circle. Okay, so Yosemite is a national park. That means Yosemite has to lie within the national park circle. So it has to be in here somewhere. Is there any way it could be in the cool circle but not in the national park circle? Well, no, it is a national park. And so it has to be in the red circle. So there's only one way I could draw this. Only one real way I could draw this. Let's use green, because national parks are kind of green. Most of them are green. So let's call this Y. Yosemite, it's a single entity. It's one particular national park, so I use a dot for that instead of a circle. A circle would kind of represent a whole set of things. This is just one particular thing. So this one particular thing lies within the national park circle, and that lies within the cool circle. So is Yosemite cool? Does Yosemite have to be within this blue circle? Absolutely. There's no way around that. This has to be true. So this, I would say, let's just write this off to the side somewhere, that Yosemite, just write down what I just said. Yosemite must lie within the cool circle so it's valid. So it is valid, or it's valid. This would be a valid syllogistic argument right there. All right, so let's move on to another example here. And yes, I'm going to have some fun with this one. All right, is this valid or invalid? Here's the argument. You may be totally perplexed. You'll notice they all got fish in their mouth. Here's the argument. All bears like fish. All bears like fish. Even Bear Grylls likes fish. All bears like fish. Gollum likes fish. Therefore, this argument's going to go, Gollum is a bear. We're going to see if this is valid or not. So all bears like fish. Gollum likes fish. Therefore, Gollum is a bear. Huh. Interesting. Okay, so let's draw our universe again. Use a rectangle. Use black for that. And that'll be right here. So there's my universe, and let's draw in now some of our circles. So if you ever see an all something, that's a good place to start again. So let's do that. First of all, we'll go with red this time for the all bears like fish. Make a circle. Make that kind of big. I thought I picked red. Come on. There. I picked red. And let's see, all bears like fish. So I'm going to have a circle within a circle. I'll go with red for one circle, and I'll go with blue for the circle within that circle. Okay. And they don't have to be perfectly concentric. It's okay. So I can leave it like that if I wanted to, but just for the sake of easiness on the eyes, I'll put them concentric as best I can. And so this one, we're saying all bears like fish. So all bears here are within the fish circle, you might say. So all bears, all B, are within the fish circle. We'll call the fish circle F. So all bears are within the context of liking fish. Now Gollum likes fish. Gollum will go with green for Gollum. So Gollum likes fish. So that means he has to be somewhere within this red circle. Does that also mean he has to be somewhere within the blue circle? Well, maybe, but not necessarily. We are trying to draw, if we can draw an invalid way to show that the argument doesn't have to work, that's what we want to try to draw. So if that's possible, which is definitely possible in this case, I could have Gollum being out here. He still likes the fish, but he's not within the blue circle. He's not within the bear circle. And so that right there, that could be Gollum right there. And so from here, we look at that and we say, we can get our answer there. We can write down some things that Gollum does not have to lie in the bear circle. To be in the fish circle. To be in the fish circle. So the argument is invalid. So it's invalid. And oh, what's this? Is that Gollum? Hey Gollum, how you doing?
Stupid Mr. Wagner's saying I'm not a bear. This is despicable. The stupid hobbit says they stole my fishies. My precious fishies.
Gollum, you need to calm down. You need to go. You need to leave, okay? Okay?
You're going to make me leave? You're going to make Gollum leave? Smeagol's not very happy with you right now.
Smeagol, I don't care. It's time to go.
Okay. I'm going to go look for my precious.
Okay, you go ahead and do that. Alright, here we go. Moving on. Alright, no apples. Let's start with that. No apples are citrus fruits. We don't need to know what citrus fruits are just to make an argument. We're just saying what it is. So citrus fruits, this, as far as I know, is actually a true statement, but we don't need to know whether it's true or false to see if the argument would be valid. We're just saying if this was true and this next part was true, this part, would it have to follow from those things? So all Granny Smiths are just a type of apple. So all Granny Smiths are apples. And we're going to say therefore no Granny Smiths are citrus fruits. So does this have to follow? If these two things were true, does this conclusion have to follow from these premises? So let's draw another Euler diagram. And we'll bring back the rectangle. Let's see if I can get this right the first time around. It's black now. All right, good work. Good job, Mr. Wagner. Thank you. And we'll put a U for the universe. Alrighty, what's going to go in here? So if you see something like this again, all Granny Smiths are apples, that's somewhere where that should be easy to fill in. No apples are citrus fruits. So I'm going to go with A for apples, C for citrus fruits, G for the Granny Smiths. And since no apples are citrus fruits, we haven't seen that before yet in the context of what we've been doing here. But that would just look like something like this. We would have, nope, did it again, there we go. We would have something like this, and we would have something like this. So they have nothing in common, in other words. No apples are citrus fruits. We're going to put our apples in one of these and put citrus fruits in the other one. So let's go with blue for the apples. We'll say that's my A. And then we'll go with the red being the citrus fruits. So here's my C. Nothing in common. They're disjoint sets. And then all Granny Smiths are apples. So apparently, and I got my green, I saved it for Granny Smith. This is a Granny Smith apple right there. How convenient. Didn't even plan that. But that's blue. Okay, green. Didn't I select that? Really? Really? Oh my gosh. You might be able to tell that I'm feeling a little better than I was. Just sounding better. Getting over being sick than I was in my previous lesson. So a little more lively tonight as I'm creating this video here. But here's A, here's G. G lies completely within A. Granny Smith's completely within the apples. And so this is the only way I could draw this. There's no other way I could draw this. It has to be this way. So is this true? No Granny Smiths are citrus fruits. Well, Granny Smiths, do they have anything in common with the citrus fruits? No, they don't. So this would be a valid argument. So let's write down what we got here, put it all into a kind of a sentence form to finish this up. Granny Smiths, and we had to give a kind of a reason for why this has to be this way. They must lie in the apples circle. And if we want to get fancy with it, which I'll do right here, and apples. I don't know if you can hear that siren. A siren is going off outside. It'll be interesting to see if that comes up on the video. Apples and citrus fruits are disjoint. So that's my fancy word there. They are disjoint. They have nothing in common. So it's valid. Okay, siren's still going. Moving on. Oh my gosh, that is one ugly looking creature. And that's a cool looking bowling ball and some cantaloupe. Alright, so what is all this coming from? Where am I going with this? So that is an aardvark. That's as far as I know, it's like a baby aardvark. So all aardvarks are bowling balls. And this one's going to sound pretty ridiculous, but just bear with me for right now. All aardvarks are bowling balls. Some bowling balls, here's a new word we haven't seen in our logical arguments here. Some, within the syllogistic arguments, some bowling balls are cantaloupes. Again, just kind of weird, but right now we don't have to worry about how weird it is. We're just seeing if the argument is valid or not. We're not saying that these are actually true statements. We're just saying that if these were true statements, would what I write last here, would the conclusion have to follow from those being true if they were true? So if some aardvarks are cantaloupes. Some aardvarks are cantaloupes. Alright, so let's go back to it. Let's draw another Euler diagram. So here I will use black, alright, and make another rectangle. that should be big enough for what I need it for. Let's put my universe in the corner. Let's make some circles. So what do I want to do with these circles? All aardvarks are bowling balls. I'll start with that. That's pretty easy to draw in there. And let's go with blue and red again. So all aardvarks are bowling balls. So let's call the blue circle aardvarks. And let's call the red circle, make a red circle here. Call the red circle. Make that a little bigger and then move it in just a second. Let's call the red circle. No. There we go. Let's call that red circle bowling balls. Oh, I almost had it. Red circle, red letter, here it is, red circle, red letter. So A is completely within B, aardvarks completely within bowling balls. Now some bowling balls are cantaloupes. Alright, so what does that look like? Some bowling balls are cantaloupes. Let me use, this time I'll use orange so you don't think it's because this is green that's going to be green. This matches up better with the color of the cantaloupe. So some bowling balls are cantaloupes. Some bowling balls would be cantaloupes. So that means they would have to intersect somewhere. They'd have to have something in common. It could be that all bowling balls are cantaloupes. So it could be like the whole circle. It could be, that is not a circle tool. That is, now I should have the circle tool. Okay. So it could be like that. It doesn't have to be, but it could be like that. It also could be like that. I would have some bowling balls or cantaloupes. They would have something in common. And it could be something like this. And let me see if there's anything else I'm not thinking of. It could be something like this too. So one of those four things. If you look on page 157, example 5 in your books, not here, example 5, but example 5 in your books, it shows you the drawings of all four of those. So I'm going to go back to, I'm going to show you the one where it doesn't hold. Right there is the one where it doesn't hold. And I've got a little more space over here, so I'm going to put that over here. So here, B and C, bowling balls and cantaloupes have something in common. I use the A, B, and C because that's what your book has for example 5, so you can look at that as an example that matches up with this one. So A, B, and C, cantaloupes, bowling balls. Here I could have, I'll draw a little dot in there. Some bowling balls are cantaloupes. So right there would be a bowling ball. That would also be a cantaloupe. If I had a dot right there, I would have, there's maybe another one. There wouldn't have to be two, but maybe there's a second one. There's at least one though. So I'll include at least one little dot there and say, hey, there's one. But is that necessarily, is an aardvark necessarily have anything in common with the cantaloupes? Well, no, this and this don't have anything in common. They don't have any intersection at all. So this, they could have, the other possibilities I drew would have that having some intersection, something in common, but they don't have to have something in common. So whenever we can draw an invalid way where the premises are true, but the conclusion is false, that's what we want to try to draw. So we want to draw something where the premises are true, which is true based on what I have in this picture. I have all aardvarks are bowling balls. I have some bowling balls are cantaloupes, but that doesn't necessarily mean that this follows from that. So let's write down what I just said verbally. Let's write that down, and so we have that in our notes here. So this diagram would satisfy the given premises showing, W a little better, showing the argument doesn't have to be true. So showing the argument doesn't have to, it could be true, but it doesn't have to be true. It doesn't have to be true. Make that a comma. So the argument is invalid. So the argument is invalid. That would be my final answer there, invalid. So I'll box it in. So again, look on page 157 in your books, example 5 in your books, to see all 4 possible drawings. Again, I kind of held the circle in place for a few seconds and showed you all 4 possibilities that way too. Let's move on to what will be our final example. And so here's turkeys, hot dogs, and some beef over here. Let's write these things down. So sometimes you could have, instead of 2 premises like we've been having all along, sometimes you could have 3. You could even have more than that. We're just going to do a final one with 3. So let's say that some hot dogs are made of turkey. Some hot dogs are made of turkey. And let's also say that this is one of our premises. All things made of turkey are edible. So we can, according to this, we can eat anything that's made of turkey. And some things I find this funny, but some things that are made of beef are edible. Only some things. I'm not saying again that these are true or false statements. I'm just saying that these are the premises that we're gonna use to see if the argument's valid. So some things that are made of beef are edible. And all that to say, therefore, some hot dogs are made of beef. Does that have to be true if these 3 premises were true? That's what we're trying to figure out. So let's draw a universe again. One final time here. And this one, that should do it for me. There, we'll call that U in the corner for the universe. Okay, and let's start with wherever I see all, that's always, almost always the best place to start. So all things made of turkey are edible. So within the edible circle, we'll do that in blue. Within the edible circle, I'm going to have a turkey circle. So within the edible circle, there's going to be my turkey circle. So all things made of turkey, all no, had to mess it up one more time. There we go. All things, there's red. All things made of turkey are edible. We'll go with E for edible. Let me make that E a little clearer. Okay, so all things made of turkey is totally within the edible circle, according to this up here. And now we're going to say some hot dogs are made of turkey. Some hot dogs are made of turkey. So here's one way we could draw that. Some hot dogs, well, let's go with orange for the hot dogs, because sometimes that's the color we see of hot dogs. Hot dogs are some interesting colors. I remember when I was close to finishing the Appalachian Trail, I got this hot dog at the last store I could get it at. It was just one of the most disgusting things I have ever seen in my life. It had this pink coating, like not a pink fleshy color, but like fluorescent pink coating. And I was very, very hesitant to eat it, but I was really hungry, and so I ate it, and it was not good at all. I was extremely hungry, so I thought I'm gonna like this. No, that was not good at all. No. So E, T, and H, just so you don't. No, I'm okay. I'm okay now. E, T, and H. This is one possibility. So here, hot dogs have something in common with turkey. They have some intersection here that fulfills this part. Some hot dogs are made of turkey. So apparently, at least if this were the way I could draw it, I could have hot dogs being edible too. I could have this, and I think I can show that to you pretty easily here. I could have this, just because some of them are. I could do this where it's, come on, I'm just trying to move it. Just trying to move. There we go. It could be like this, or it could be like this. But I'm going to go with what I had first and say that instead. So some hot dogs are made of turkey. And now, does this have to hold true? So some things I still have to use my beef premise here. So some things made of beef, I'll go with, if I had pink for pink slime beef, maybe I'd use that, but I'm going to go with green. So some things that are made of beef are edible. So here is, I need some practice with these circle tools. I just keep doing that. So here is one possibility. And remember, I'm trying to draw a possibility where this final conclusion would not hold, would not be true. So this is what I was thinking of to make that not true possibly. Let's see if that actually works to prove that that's invalid. So this would be beef. Beef and edible have something in common. So some things that are made of beef are edible. So I have something in common here. There's at least a little bit of something here. Now does beef, some hot dogs are made of beef. Does hot dogs and beef have anything in common in this possibility? No. So it has to always be the case that this would hold. And so it's not always the case. I found a possibility where it didn't work out. So here I would have my answer. That is a possible invalid way to show that. So I could say that this would be true. So let's write this down to finish this one up. This diagram would satisfy the given premises showing that the argument doesn't have to be true. So same sort of wording as before. So showing that the argument doesn't have to be true. So the argument is invalid. So the argument is invalid. So same basic thing as the last example in this case. And let's write down one final tip. So we've said this several times. I've said this several times in this. You always want to try to draw something where the premises hold but the conclusion is false. So you always try to draw, there we go. Always try to draw, I think I'm just trying to write too fast there. Always try to draw the Euler diagram to show the syllogistic argument is invalid. So you're always trying to draw it where the syllogistic argument is invalid if possible. So the premises, what you have in the premises, that has to be drawn correctly. So what you have in the premises here, what you had in the premises here, you have to draw it in such a way that it actually holds. So like we did here, like we did with all of them, it actually has to hold. You can't change the premises around, but you're trying to do that where the premises are true, but the conclusion doesn't necessarily follow from that. If this isn't possible though, so if this isn't possible, the argument must be valid. And you know what? I just saw a mistake I made. I said the word invalid, I believe, but I wrote valid. So that's why I got an eraser. So the argument is invalid. So always try to show that the argument is invalid. This isn't possible. The argument must be valid. And so Gollum, I told you to leave.
I didn't want to leave.
Gollum, you need to go now. Gollum, you need to go. Gollum, don't, oh my gosh, what are you doing? Gollum, come on.